So good morning, everyone. Welcome back to Math 115. Your final exam is coming soon. Final will be Tuesday, December 6th, in this room at 9 a.m. Okay, that's the Tuesday, Thursday classroom. So 30 minutes later than our class usually starts. We are going to review today. I have posted the last two reviews, i.e. Office Hours Tuesday and class yesterday, to the YouTube. I'll try to post today's lecture pretty soon after I finish up here today. And then also this afternoon, we'll have an office hour session in LeConte 109. So review today in class and in LeConte 109 at 2:30 to 4 p.m. If you missed it, we had an anonymous tip on the survey which said they wanted an option to have a quiz 7 grade if they wanted. So I said that's fair. So I posted an optional assignment onto Blackboard, okay, which you can do in lieu of a quiz 7 if you want to have 7 quiz grades, okay? So in that case, your 7 quiz grades would be made up of the 6 we took in class plus this optional assignment, and it would follow the same mechanism of drop the 2 lowest scores. So if you have like a really low quiz average or something like that, that would be a good thing for you to do, is the optional quiz 7. I think your last homework assignment is 5.5 and it's due today, right? Okay, so that's the last one. And yeah, okay. Any administrative questions before we start in on content for today? Oh, this thing's not so easy to open. Jeez. What is going on? Okay. Need the precious liquid inside. Okay. So, with that in mind, I'll open up the floor to any questions that you all may have. So, if you have been studying and come across some problems from the homework that you're like, oh, I don't really remember how to do that, now would be a great time to ask me about them. So anyone have either a specific homework question or a generalized kind of topic they want to talk about? Andrew?
I don't know if you guys covered this on Tuesday, but there was one on the exam that was like, if secant or sine is this and tangent is less than 0, what is secant?
Yeah, anyone have their exam on them? What is that problem again? It's something like sine is like 12 over 13. Is that what you're talking about?
Yeah.
I think I remember it. It was
12 over 13, tangent is less than 0. Find the exact value of sine.
and we're supposed to find secant of theta? Okay. So this problem should be familiar to everyone. There were several of these on the homeworks, and then also one on the exam. So someone help me out. How do I start something like this? I know that sine of theta is 12 over 13 and tangent of theta is less than 0. What's maybe the first thing that I want to do? I want to draw my unit circle and I want to draw what this angle looks like. What can I surmise about the angle theta based on this information? Yes?
Sine is y over r, and it's in quadrant 2 or 4.
2 or 4. Okay, so we're getting onto the right track here, thinking about which quadrant, right? Which quadrant could this angle live in, right? Because we see sine is 12 over 13, which is a positive number, right? So what does sine represent in terms of the point on the unit circle? Yep.
Height.
The height, right? So what do we know? We know that the height of the point is 12 over 13, which is a positive number. So actually, I would conjecture that we're not actually going to be in quadrant 4, because points that are on the unit circle in quadrant 4 have a negative y value. So how could we sort of take sine of theta equals 12 over 13 and eliminate 2 of the quadrants? We can eliminate the 4th quadrant because y points on the unit circle in the 4th quadrant have negative y values. And likewise, we can eliminate the 3rd quadrant. So actually, I would say that we're either in the 1st or the 2nd quadrant. And then that's the sine information, has now been parsed. What's the other one say? Tan theta is less than 0. Can that help us to determine between 1 and 2 where our angle lies? If tan theta is less than 0? Which quadrant are we in? We're in 2, quadrant number 2, right? Why? Because of ASTC. All trigonometric functions are positive for angles in the 1st quadrant. Since tangent is not positive, it's negative, we know we can't be in the 1st quadrant. So by process of elimination, sine theta equals something positive means I have to be in quadrant 1 or 2. And tan theta less than 0 means I have to be in quadrant 2 or 4, right? Okay, I have to be in quadrant 2 or 4. Oh, so you were probably going with the tangent first. Okay, now I understand. I was a little confused at first. Yes, okay, good. So between those two, it has to be in either 1 or 2, and it has to be in either 2 or 4. Okay, the only one which is common between these two is quadrant 2. Okay, so this is all to say that the angle is going to be somewhere in quadrant 2. And what is the angle going to look like? Well, we can make a pretty good picture based on this number, which this number is like pretty close to 1. Okay, pretty close to 1. Which means that the height 12 over 13 is like, okay, here's 1/2. Right? And here's 1. 12 over 13 is probably like pretty close to 1. So I would say this triangle is going to look something like this. Okay? Something like this. Okay, and now our goal is to find the coordinates of this point. But this is clearly not a 30, 60, 90 triangle or a 45, 45, 90 triangle. It's a much sharper angle than that. Or much more less sharp, I guess, because if you're talking about this angle. Anyways, how am I going to figure out what are the coordinates of this point? Well, I know the y-coordinate is 12 over 13. But how am I supposed to figure out the x value if this is not a 30, 60, 90 triangle and it's not a 45, 45, 90 triangle? Set it equal to y over r. So, okay, yes, this is the famed homework problem, okay? Or rather, the homework problem, like, help tells you to do this kind of like y over r thing, which I guess if you have like a big triangle like this, it's going to be a similar triangle to this one. But I guess if you think of your triangle as being this one, then r is just 1, right? R is just 1. So y over r would just be y. But how can I figure out what this number is? We don't have our 30, 60, 90 or our 45, 45, 90. Yeah, Lauren? Good. The Pythagorean theorem is what I was going for there. You may have been talking about the same thing and I just not familiar with that terminology. So, okay, what does the Pythagorean theorem say? It says that x squared plus y squared is going to be equal to 1. And this is x. Right? This is x here. So we can figure out what x is by doing the following. I'm going to do x squared plus 12 over 13 squared is equal to 1, and therefore x squared plus 144 over 169 is equal to 1, and therefore x squared is equal to 25 over 169. It's 169 minus 144. Okay, so the right-hand side can be written 169 over 169. And then we subtract from 169 144, and we get 25. So then we have x is equal to the square root of 25 over 169, which also plus or minus, and then that's equal to plus or minus 5 over 13. Okay, so we got two answers. Which one is correct?
Negative,
The negative one. Why?
because it's less than 1.
Yeah, we're in the second quadrant. Okay? Points in the second quadrant have a negative x value. This is why we choose the negative one. So get rid of that positive one. So this is x. So is that my solution? No, not quite. What was I supposed to do? Once we get here, we feel like, oh, we've done so much work. Aren't we done already? But what does the instructions say? It says find secant of theta. Secant of theta is equal to 1 over x. So that would be equal to 1 over negative 5/13, which would be negative 13 over 5. Now I'm done. Okay, so that's that problem. It goes into a class of these trig problems where, look, at a certain point you come to realize that sometimes you have the use of certain tools available to you and sometimes you don't. And when you have been like shut off from some of your more useful tools, you know you have to use the other tools. So the two tools which we have basically for solving triangles are either it's a 30-60-90 or a 45-45-90, or the second tool is the Pythagorean theorem. Those are the two tools that we have for solving for the side lengths of a triangle. So you know if you can't use the one, you have to use the other, is what I'm trying to get at there. So yes, even though these triangles live inside of the unit circle and there's this associated angle and all of that stuff, I don't want anyone to forget that it is just a triangle, right? It is just a triangle, and you can use the Pythagorean theorem to solve for the side lengths, as long as you know two of the side lengths, which you do. You know one of the side lengths is the sine, and one of the side lengths is always 1. That's sort of the benefit of having this triangle inside the unit circles. You always know the hypotenuse will be 1. Okay, so any questions on this one? All right, final recap. First, we determined which quadrant the angle was going to live in. And then we drew a rough sketch of it. We made the triangle. We went to the point and we surmised that we wanted to find out what the x value is so that we could do secant of theta, which is 1 over x. So we need the x value. We don't have it, so we need to solve for it using the Pythagorean theorem. That was easy enough to do, except it gave us two solutions. So we had to be a little bit careful about which one was the correct answer, which we selected the negative one because our point is in the second quadrant. Second quadrant points have negative x values. And then we just did the reciprocal in order to get secant. Okay, so next question. Or next topic, if someone wants to talk about a topic. Yeah, Haley?
It's a question from quiz 5. Find the domain of the function for f(x) equals log x minus 1 over x plus 2.
Okay, great. So find the domain of log of, and what was inside again?
X minus 1 over x plus 2.
Great. Okay, so let me have a brief aside. The aside is to talk about the domain of the function f of x equals log x. And to talk about this, we need to again have another aside, which is to talk about the domain and range of the inverse to that function, which what is the inverse function of log x? It is the exponential function, e to the x. Okay, so I don't know, if you want to put ln here, that's fine. Log to me means ln. Let me put ln. Actually, I guess it doesn't really matter, does it? Why don't I do this in generality with log a, and then we'll call this log a, and then we'll put in here a to the x. Maybe that's even more general. Okay, what is the domain and range of the inverse function, a to the x? Well, you know what the graph of a to the x looks like. Okay, when x is super negative, this will look like something like 1 over a to the negative big number, or sorry, positive big number, which would be like a really small number. But importantly, this number is still greater than 0, right? Which is why you observe the graph of an exponential function looks something like this, right? It has an asymptote at y equals 0, right? So no matter what power you do, okay, if I'm doing like 3 to a certain power, there's no way for this number to ever be a negative number. Okay, there's no way for this to ever be a negative number, right? Because we take a positive number to any power. Negative powers just mean we divide by 1 over 3 to the power, right? Whatever that power is, if there was a negative here. So this is why we observe the graph looks like this, which you can tell that the domain, okay, you can do any power of a that you want to do. 0 is fine, negative numbers are fine. The domain of a to the x is all real numbers. But the range of a to the x is what? Be brave. Yeah, 0 to infinity. And should I have a bracket or a parentheses? Parentheses, right? Because there's no way to make this number 0, no matter what you put in for x. Okay, so this is the domain and range of the inverse function. So if we're going to go back to green mode now and ask ourselves what is the domain and range of log a of x, what's the domain going to be? Yeah, it's the range of the inverse function. These two functions, you basically swap the inputs and outputs, right? So if the range is the collection of outputs of the inverse function, then that set of numbers will be the domain of the inverse function. Okay, so the domain will be 0 to infinity. And the range will be all real numbers. And you can see this in the graph of the log function, log a of x, which looks like this. Okay? So let me also take this opportunity to remind you of the 2 points with which an exponential function always goes through. Those are the points 0, comma what? What happens if I plug in 0 for x here? What would I get? 1. Good. Anything to the 0 power is 1. Okay, and now let's try this one. If I plug in 1, what would I get? Just a. Okay, so this is 1 comma a. So what are the 2 points which are always going to be on a logarithm function? Not 0, 1, and 1a, but good, 1, 0, and a1. We swap the inputs and outputs. So here is the point 1, 0. And then also we have the point A1. Okay, so now we have finished our aside, which our aside was to talk about the domain of log A of x, right? Log A of x. Our problem is slightly more complicated than that, right? This function is what's called a composition, right? A composition of functions is when you plug one function into another function. In this case, the outer function is log A of x, and the inner function, which is being plugged into log A of x, is this rational function x minus 1 over x plus 2. So, in order to do the domain of this guy, we need to have two considerations. Number one, x needs to be in the domain of inner function x minus 1 over x plus 2. That's step one. We must have this to be true, okay? Step two is x minus 1 over x plus 2 needs to be in the domain of the outer function log A of x. Okay? Are we happy with the setup at this point? If we can find all of the numbers x which satisfy these two properties, that will be the collection of numbers which I am allowed to plug into this function. Any questions so far? Okay, then let's see here. I need to find out what numbers will cause both of these two things to be true. Well, x, we said, needs to be in the domain of the inner function, which is this. What does that tell us that x should never be? Yeah, x should never be equal to negative 2. That's what we learned from the first part. Okay, so as long as x is not negative 2, we can compute this part. And then we can move on and ask, is that an acceptable input for the log function? Okay, so this is why we sort of discussed what was the domain of the log function. So if we're going to plug this number into the log function, we need that number to be in the domain of the log function, which means x minus 1 divided by x plus 2 needs to be a number which is in the interval from 0 to infinity, because that's the domain of the log function. Another way that you could rewrite this would be x minus 1 over x plus 2 needs to be larger than 0. Okay, I don't like my greater than signs today. That's a little better. Okay. So this is how we set it up. Are there any questions about how we have set this up until now? Okay, then let me ask you all, what is left to do? Yeah, we have to solve this inequality, right? We have to solve this inequality. And the method which we're going to use to solve this inequality, Lauren gave it to me already. It's the test point method, okay? Anytime that I have an inequality which is like more complicated than just a linear one, which a linear one would be something like, 7x minus 2 larger than 0. Okay, that's a linear inequality. If we have something more complicated than that, like if there's a square here, or if it's a rational function, or trig, or something like that, then we're going to use the test point method. Okay, so how are we going to do the test point method to solve x minus 1 over x plus 2? What needs to go on my number line?
-2.
And what else? 1. Good. Okay, and then now what's my game? Lauren, what am I supposed to do with the test point method?
Plug points in each.
Okay, which ones should we use, do you think?
-3, 0, and 2.
Okay, good. Those seem like good ones to me. Here's why I like Lauren's choice. I really like -3, 0, and 2 for the following reasons. What I want to do with those points is plug them in here, okay? I like using nice whole numbers because it's easier to do arithmetic with whole numbers, okay? I like using 0 the best because then I just, ignore the x's here, right? That's why I like using 0 the best. So let's plug them in. And what am I supposed to do? I plug them in, -3 minus 1 over -3 plus 2. I'm supposed to check, is it larger than 0 or not? And let's see, this would be -4 over -1, which would be 4. So I think it's true here, right? So I'm going to shade because it's true. If I plug in 0, I'm going to get -1/2. Okay, if I plug in 0, I'd get -1/2, which is not larger than 0, so it's false in this region. And then again, it's going to be true over here because 2 minus 1 over 2 plus 2 is 1 over 4, which is positive. So it's true here. We shade. And there's only one thing left to figure out, which is what am I supposed to do at -2 and 1? I need to decide whether I'm going to have an open circle or a closed circle for each of them. How about -2? Open circle. Why open circle?
Because filling that in for x is not going to be greater than 0.
Exactly. What would I get if I filled in -2 for x? I'd get an error, yeah, or I would get undefined, right? So it's definitely not giving us a number which is larger than 0. It's not even giving us a number. So I'm not going to fill in here. I'm going to do an open circle. And then at 1, what would I get? I would get 1 minus 1 over 1 plus 2, which would be 0 over 3. Larger than 0? Question mark? No, why not?
0 isn't greater than
Yeah, there we go. 0 is not greater than 0. Okay, so let's have an open circle here. Okay, so now we have basically described the x values which cause this to be true. You could say x should be in the interval from, what would this, how can I translate this into interval notation?
negative infinity to -2 with a union of 1 to infinity.
And what kind of things am I going to put here? Brackets or parentheses? Parentheses because they're not included, exactly. Okay? So, what do I need to be true? First of all, I need x to not be equal to -2. And, second of all, I need x to be in this interval. But these two things are compatible, actually, because -2 is already not in this interval. So, if it was, I would have to, throw it out artificially. But as it stands, this is what I would call the domain of this function log a of x minus 1 over x plus 2 is this collection of numbers. Any comments on that, Haley? All good? Okay, so recapping, the thing that you have to be worried about with a composition of functions, finding the domain, you first need the x value to be able to plug into the inner function. And then on top of that, you must have that the output of that function needs to be an acceptable input for the outer function. Okay, so two things that have to both happen. We're only going to take x values that cause both of those things to be true. Namely, the x value needs to be in the domain of the inner function, and the output after you plug that x value in needs to be in the domain of the outer function. So then you solve for the collection of x values which make this true, you solve for the collection of x values which make this true, and you take the, not the union, but the intersection of those two sets, namely those points which cause both of the things to be true. It's an and type of situation, not an or. Okay, and then we get this collection of points here. So any questions on that example before we move on to something different? Okay, doesn't seem like there are, so should we talk about something different? Maybe another problem? Yeah.
For test 2, the fx equals c times a over x type equations.
Like this?
Yeah.
And I'm assuming it goes through 2 points?
Yes.
Okay, so what are the points?
1 and 1, and then 2 and 6.
Okay, so this was one of those problems that came back again and again and again. So we have an exponential function, c times a to the x, and what is our goal for this type of a problem?
Put it into that type of function.
Sorry?
Put it into that function.
Well, yes, but more broadly speaking, at the end, what should our answer be? I.e., what do the instructions say? They say something like, find the function of the form.
That contains 2 given graph points.
Okay, so find the function of this form. What does that mean my job is to do?
Wouldn't you have to graph it?
You are going to have to graph it, but broadly, I'm looking for the answer of why we want to graph it. We want to graph it so that we can ultimately accomplish what? We should always begin problems with the end in mind, right? What is not known here that I'm supposed to find out? Yeah, A and C. That's what I need to do. So we should always start by asking ourselves, what am I trying to do? Because otherwise you're just kind of blindly walking in the desert. You don't have a selected location in mind, right? So select the location of where you want to go first. So down here I'm going to write, ultimately my answer will be something like C equals and A equals, and I want to find these two numbers, okay? That's what I want to do. So to that end, I think it's a good idea to graph this function. So let's try to graph. We know it's an exponential function, and we know generally what the shape of an exponential function is, and we know how to graph these 2 points pretty easily too. 1, 1 is right here, and 2, 6 is somewhere up here. And so we're going to have an exponential function which is looking something like this, right? So let's see if I can do that. Oops. Okay, this is an exponential function that looks something like that. Great, so I have the graph now. Now what should I do? Or what's something that I could do? It doesn't have to necessarily be that I should do it, but what's something else that I can do? Sorry?
Plug in the x value.
Yeah, plug in the x value. Is that what you were going to say, Gavin? Okay, plug in the x value. So by the x value, I assume you're talking about one of this one or this one. right? So let's plug it in to the function. The whole deal with the graph of a function, okay, is that how do I get the height of the point? I'm going to take the x value and I'm going to plug it into the function. That will tell me what the height of the function is. Okay, so for this one, it's telling me, look, if you plug in 1 here, then the output will be 1, because that's why the height of the function is 1. So this tells me that c times a to the first power is equal to 1. And I can do the same thing with the second equation, which says c times a squared is equal to 6. Okay, so this is testing a couple of things. I mean, the graph can help you visually to identify what's going on, but really this is a question of, do you know what it means for a point to be on the graph of a function? What it means is that if you take the x value and you plug it in, the output will be whatever the y value is. That's how graphs work, right? So that's what it's testing, and it's testing whether or not you can sort of derive these equations from this fact that this is your function and it goes through this point. Then you can make this equation based on the input and output of the function. Okay? So now we have two equations involving two variables. How do I figure out what one of the variables is?
That's a good question.
That is a good question, right? That's really the crux of it, isn't it? Well, any ideas?
For the one on top, the c times a equals 1, if you divide by a on both sides, and then you plug it back in
Yeah,
the second one, then you can get the answer for c.
exactly. So there's two ways we can solve this. I'll show you both ways.
But you can answer right.
The first way, let me move that down. Okay, way number one, Griffin's way, is actually called substitution. What we are going to do is solve one of these equations for one of the variables and then plug it into the other one. So we can rearrange equation 1, can be rewritten as c equals 1 over a. Yes? C equals 1 over a. And then I'm going to plug c equals 1 over a. I'm going to replace c by 1 over a in the second equation. So equation 2, we will do 1 over a times a squared equals to 6. And then we can simplify the left-hand side to just be a. So a is equal to 6. Now what do I still have left to do? You want to finish it off, Griffin?
Then you just plug that into the first one.
Yeah, you can take this and plug it back into either of these equations to solve for c. So now I'm going to go back to equation 1, and I'm going to do c times 6 is equal to 1. So what is c going to be? It's 1/6. So now we said, what is c? It's 1/6. What is a? It is 6. Okay? So that's Griffin's way, which is called substitution. We call it substitution because we solve for c, and then we substitute. I know something that c is equal to. I'm going to replace or substitute c by the thing that it is equal to. Okay? That's why it's called substitution. Way number 2 is a little bit different. You say, look, these two numbers are the same, and these two numbers are the same. So if I divide one number by the other, it's the same as dividing what they're equal to by what they're equal to. So you divide equations. So we're going to do EQ2 divided by EQ1. You can literally just write it like this. CA squared equals to 6. Divide that by CA equals to 1. Then what do you get? You get the equation the c's cancel here. One of the powers of a cancels, and you get a is equal to whatever 6 divided by 1 is, which is 6. And then once you have that, you're going to substitute back into equation 1, like Griffin did at the end. C times 6 equals 1. C equals 1/6. Okay, so two different ways which you can visualize the ending of this problem. Okay, so that's it. What did we do? We started with the function and we identified what we are supposed to do, which is to find out what are the numbers c and a. That's what it means when it says find the function of this form. X is the input, so x is going to end up being just x, but we needed to know what the other numbers are, namely c and a. In order to do that, we need to use the information which is given to us, okay? Whether you want to visualize this information in terms of two ordered pairs, or if you want to visualize it in terms of the graph, that's up to you. But what we need to be able to do is to derive two equations. CA equals 1. That comes from taking 1 as the input in this function. We know the output should be 1 because we know that the y value is 1. The way you get the y value is by taking the x value and plugging it into the function. Okay? So this is how we get these two equations, and then from there it's solving two equations and two unknowns. Okay? And that's all we have to do to finish it off. Any questions on this example? All right, then next question. Yep.
There was a question of homework 3.4, and it's about solving exponential equations.
Okay.
And it's 2 times 3 to the power of x minus 2 is all equal to 11 to the power of x plus 2.
Okay, this is a good problem. What question is this on the homework, do you know?
14.
Okay. Thanks for your question. This is a great one. Okay. So, I want to get x by itself, but dagnabbit, where is x right now? It's in the exponent. So, that makes me think I want to get it out of the exponent, don't I? How do I do that? Yeah, natural log is how I do that. It's 2 times 3 to the x minus 2, like so. Yeah, we can still do this. Okay, that's going to throw a wrench in things, but I think we can avoid it. So normally what you would say is like, look, we want to divide by 2 on this side so that we can, have this thing alone when we take the natural log, right? But you're going to notice that you're either going to have a 2 here or you're going to have a 1/2 here, right? Those are the options. So actually, I think we're going to have to just go ahead and do the log and see what happens. So let's go ahead and apply the natural log. On the right-hand side, we're quite happy, aren't we? We're quite happy because we can just go ahead and take the power down. So this is x plus 2, and always we're going to use our parentheses. And then we have ln of 11. So this is kind of like a harder version of the problem that we had on the exam. Okay, and how about the left-hand side? Can I go ahead and take this down? Can someone offer an explanation? Why not? Why can't I just take this power out?
Because the power function doesn't cover both.
Exactly. The power only applies to part of the argument. If I wanted to pull it out like so, I would need to have some parentheses here. Or else I would need to have an x minus 2 here, okay? The power has to apply to the entire argument in order for us to pull it out. But it's only applying to part of the argument. So, am I doomed to fail, or are there any other actions that I could take here. I know, everyone always wants to say they're doomed. We're not doomed. I think there's something we can do. We want to focus on trying to rewrite the left-hand side. Any ways we could rewrite that?
Oh, ln2 plus ln3 x minus.
Is that what you were thinking too? Yeah, so there's all those other rules for logs, like log of a quotient or log of a product. Here we have a log of a product. You can rewrite the log of a product as the sum of the logs. Why is that better than what we had before? Yeah, now we can pull the exponent out. So ln2 plus x minus 2 times ln of 3 is equal to x plus 2 times ln of 11. Okay, so this is looking marginally better. How can we take it from here? Well, what kind of equation is this, really? It's like a number times x plus some other numbers is equal to a number times x plus some other numbers. This equation is linear. It's no different than something like 2x minus 7 equals x plus 3. How do we solve linear equations? Well, specifically, we want to get everything with x to one side and everything that's a number to the other side. So the way I'm going to do that is by first distributing everything. Okay. So this is going to be a long thing, but let's start by identifying what is a linear term and what is a constant term. These terms are like terms, and these terms are like terms. Okay, the ones with yellow are numbers, and the ones with pink are linear terms, meaning that they have an x. Okay, so I'm going to move all the linear terms to one side, and I'm going to move all the numbers to the other side. So that would look like this: ln of 3 times x minus ln of 11 times x is equal to 2 ln of 11 plus 2 ln of 3 minus ln of 2. Okay, so now I have everything with x on one side, and I have everything that's a number on the other side. I think just like one step left to go, but this is a really, really crucial step. How am I supposed to get x by itself? Right now it's in two places at once. I need to get it alone. Yes, we can take x out of each of these terms, like so. Okay, like a GCF, okay? It's a GCF here. Take x out. Is equal to 2 ln of 11 plus 2 ln of 3 minus ln of 2. So now what is this? This is x times a number equals a number. You've been solving this type of equation since a long time ago. When you solve something like 7x equals 14, what do? Just divide both sides by 7, right? So if I have x times a weird-looking number equals to a weird-looking number, the process is still the exact same. we just divide both sides and leave it as it is. We write x equals 2 ln of 11 plus 2 ln of 3 minus ln of 2, all divided by ln of 3 minus ln of 11. Now we're done. Oops. Okay, so that's this problem. Pretty challenging problem, I think. It's like the one we had on the exam, except the one on the exam, we didn't have this extra 2 here. So, you know, what I think a lot of students find challenging about these types of problems is the presence of the ln's really bothers people. And they get a little confused where they're like, it just like, for whatever reason, it doesn't key in as like a number, but it's just a number. And the only unfortunate thing is that we can't combine these numbers as easily as we can combine numbers like 3 plus 4 equals 7. Okay, if you have ln of 3 plus ln of 4, there's no good way to like combine those numbers into a nice shiny new number. Okay, so we just leave it as like in this sort of abstract sum kind of notation. So any questions about this one? All right, we're hitting a lot of content here. I like this. Next question or next topic? Or if you want, I can try to find something. Let's take a look. I'm trying to think what we have not really talked about. Okay, I thought of one, actually, that I want to do just off the top of my brain. How about something like this? Compute cosecant squared of 6,056 pi over 6. Okay, so you know this is one of those crazy angles, right? It's one of those crazy angles that if I were to draw my unit circle, what does it do? It goes around like 1,000,000 times. Not 1,000,000 times, but like 1,000 times. And then it ends up somewhere. Right? It ends up somewhere after all of that. So what I do every single time with this sort of problem is you kind of untangle however many swirls there are. Okay? You untangle however many swirls there are, because you know that an angle which looks like this, okay, eventually points at a point on the unit circle, which is also pointed at by an angle which just looks like this, right? So the goal is to translate the angle into a coterminal angle, which is more easily visualized. Okay? So we had a couple of ways of doing that. Way number one was subtract multiples of 2 pi until I get something which is between 0 and 2 pi. Why is that not a great strategy for this problem?
Really big number.
Yeah, I'm going to have to do that like
Bajillion.
a lot of times, right? I'm going to have to do that a lot of times. So what's easier to do, okay, is to try to find try to rewrite this inside thing as like a multiple of 2 pi plus something smaller. The way it jumps out to me is the following. You can rewrite this as cosecant squared of 6,000 pi over 6 plus 56 pi over 6. That's how it jumps out to me at first. Because what is 6,000 pi over 6? 6,000 pi over 6 is just 1,000 pi. (1,000 pi is a multiple of 2 pi. So loosely what it says is go around the circle 500 times. Right? Go around the circle 500 times. I know I'm going to end up right back where I would have been if I just did 56 pi over 6. Okay? So then I can rewrite this. Since cosecant is 2 pi periodic, I can rewrite this as cosecant squared of just 56 pi over 6. Because if you add any multiple of 2 pi, it's going to be equal. Since 1,000 is a multiple of 2 pi, namely it's 500 times 2 pi, this represents going around the circle 500 times. And then you're still going to point at the same angle, ultimately. Okay? So that's one, but we still have an angle which is larger than 2 pi, right? But now you can go ahead and iteratively subtract 2 pi if you want, or 12 pi over 6, okay? Or also you can do this again and say, look, this is cosecant squared of like 48 pi over 6 plus 8 pi over 6, right? Which 48 pi over 6 is 8 pi, right? So this represents going around the circle 4 times. 1, 2, 3, 4. And then you go an additional 8 pi over 6. So it's going to give you the same thing as if this wasn't even here. We'd get cosecant squared of 8 pi over 6. Okay, so this is really the main part of what I wanted to explain about this problem, is this process of taking a really big angle and finding its coterminal angle, which is between 0 and 2 pi. Because it's hard for me to wrap my head around what this looks like as an angle, because, I don't know, human brains just aren't made for going around the unit circle that many times. So this is something that makes a lot more sense to me. I'd much rather do this. So let's go ahead and finish it off. Well, we can simplify the inside to 4 pi over 3, right? 4 pi over 3. Which quadrant does 4 pi over 3 point in?
The fourth.
Down here?
This way now, so. It's the third, isn't it?
Yeah, I think it's going to be the third. So here's how I like to visualize angles like this, okay? I like to think, well, this is a little bit more than 3 pi over 3. I know 3 pi over 3 points right here. And then I think, well, I need to go pi over 3 more than that. And in my brain, I think pi over 3 is 60 degrees. I'm fairly comfortable with drawing 60-degree angles. It's going to look something like that. So it's going to point maybe like down here. So the way I visualize this is my 3 pi over 3, and this is pi over 3. So the whole thing makes 4 pi over 3. That's how I like to visualize them. Okay, so this part is pi over 3. So the coordinates of this point are going to be what? This is a 60-degree angle, which means this is a 30-degree angle. Across from the 30-degree angle is a side length
1/2.
of 1/2. And then root 3 over 2. So these are clearly the coordinates of this point, aren't they? Or are they?
They both.
Yeah, both negative. Okay, so don't forget, when you solve these triangles, it's easy to think like, yes, the side lengths are 1/2 and square root 3/2. But we're talking about a point which lives in the third quadrant. Both of them should be negative. Okay. And now I'm supposed to do cosecant squared of that. Whoa, cosecant squared. Can I do that? How do I do that? Is it a problem that we're squaring it? That seems like harder than usual, right? Seems harder than usual. But what does it mean when I write cosecant squared, ultimately? It's just another way of rewriting the following. Are you comfortable doing the inside? And are you comfortable taking a number and multiplying it with itself? Yeah, I think you're comfortable with doing both of those things. So let's start with the first one and just compute what is cosecant of 4 pi over 3. How do I do that?
One over sine.
Yeah, 1 over sine. So we're using a reciprocal identity here. If you want to go straight to just doing like 1 over y, that's also fine. But we can do this, 1 over sine, and then we can rewrite that as, what is sine of 4 pi over 3? It's going to have something to do with these coordinates, right? Yes, negative square root 3/2. And then we square that and get 3/4. Okay, so I think there were two tricky parts here. The first tricky part is getting the right coterminal angle so that you can actually visualize like what this angle is doing. The second tricky part is not getting discouraged by the presence of this square here. Okay, all the square really does is it just says we're going to take whatever our answer is and square it, right? And I think you are confident in doing something like cosecant of 4 pi over 3. You take 1 over y, or you take 1 over sine, and then you know that sine is y. You find the coordinate using 30, 60, 90 triangle. You take that number, and all you have to do further is to square it. Yep.
Where did the 1 go? Like,
There's a good chance that thank you, yeah. I just dropped it because
okay, I was just like.
made a mistake. Yeah, it should be 1 over negative square root 3/2 squared, which should ultimately flip this to give us 4/3. Yep, numerical error on my part. Actually, it's not even a numerical error, it's a copy-paste error. Okay, any other questions on this one? I think we got time for one more problem. Who's got one? Or I can come up with one.
Hypothetically, in your head, what would be on the exam that you'd show us?
You know I don't do that. You know by now, because you ask me every single time, and I always say the same thing.
Exam, though.
I haven't written the exam yet, so I don't know what's going to be on it.
Well, help us out.
You make it a little nicer.
A little nicer?
Like the first exam.
Yeah, I like that.
What? The first exam was over all review.
And?
Let's do a division problem.
The trick, you teach-
Let's do a polynomial division
As our
problem.
Christmas present,
It's all A.
you'll make a nice little exam. A nice
Okay.
little one.
Or we should double the points for extra credit.
x to the 4 minus,
Like I said, 3, was it 6?
It technically gets dropped if it's lower than the rest of our exams, right?
no, the other
Or
way
it
around.
just goes into the,
If it gets higher, then one of your other exams gets replaced with the score.
Yeah, so if you had, I'll explain that in a second. 3x plus 5.
it's okay, I'll just look on the,
Yeah, so if your exam scores went like 80, 60, 70, and then you get a 75 on the final, then your total exam grades at the end will go 80, 75, 70, 75 for the final. So I'll count it twice for your final grade, and I'll also replace your lowest exam grade. So that way, if you like bombed one of the exams, or if you forgot to show up to one of the exams and took a 0, then
that happen to anyone?
I can't say anything about other people's grades in this course to you because of FERPA. So, but it's been known to happen. So that's the exam drop procedure. Let's quickly go over this problem. I got enough time to do it. What do I want to do with long division? To get the first number that, or the first term, which is going to go here,
You divide x.
yeah, I'm going to take x to the 4th, is that what you're saying? And divide it by x, okay? That gives me x cubed. And now I'm going to subtract, and of course I need to remember to use parentheses here. I'm going to subtract what I get when I multiply x cubed times these guys, which is x cubed minus 3x cubed, which gives me, okay, minus a negative, that's a plus. So this, sorry, what am I doing? This should be x to the 4th. Cancel, cancel. X cubed plus 3x squared plus 3x plus 5. And now I just repeat. Next up is going to be a plus x, ooh, this should be a minus. So this should be a minus x squared to multiply negative x squared so that I get negative x cubed plus 3x squared. Oh, that worked out nicely. So this one's going to cancel with this one, and this one's going to cancel with that one. And I'll just be left with 3x plus 5. Unless I made a mistake. Did I make a mistake, anyone? I don't think so either. Okay. This one's just going to have a remainder. So the next step is to divide 3x by x, and I get plus 3. So then I get minus 3x minus 9. Cancel, cancel, and I'm left with 14. Now what am I supposed to do?
Don't you like write the remainder as like a denominator?
Yeah, we're going to write the remainder separately. So the result of this division is x cubed minus x squared plus 3. And now I need to write something to represent the remainder. What should I write? Yes, plus 14 over x minus 3. Okay, that's how we do long division. Okay, one comment I want to make is, what am I going to do if there was no x cubed term?
You would add a 0x.
Yeah, we would replace it with like a minus 0x cubed, okay? So that we have a placeholder for when we do that long division. Okay, we'll stop there for today. Don't forget office hours this afternoon, the final review session, number 4. If you come, please bring questions. Please bring questions.